Hello and welcome to TidyX episode 53. TidyX is a screencast where we go through and explain how our code works. My name is Ellis Hughes, and you can find me on Twitter at Ellis_Hughes.
And my name's Patrick Ward. You can find me on Twitter at OSPPatrick, and you can find both of us on Twitter at tidy_explained. Or you can Gmail us at tidy.explained@gmail.com. Comment on the YouTube page if you'd like.
Subscribe.
Or subscribe. We have maybe close to 1,000 subscribers now. Or
we're just a little bit over 900. We're stoked to have so many people following us. We love that you guys are enjoying our content.
Yeah, or we have issues on the GitHub repo, so you can open an issue with things that you'd like to see. We put up an issue last week, which we're going to start to cover, and then I just put up a new issue this week. So yeah, feel free to hit us up with questions, comments, ideas, success stories. If our screencast has maybe helped you in any way.
Yeah, we'd love to hear it. Yeah, I actually heard from a friend of mine that he ended up getting a consulting gig with an episode, or from an episode a couple weeks ago, helping him show how machine learning models can be put into Shiny. And so, I mean, I love to hear that it's helping people get jobs.
Yeah, that's super awesome.
Gives us the warm fuzzies.
It keeps us uber motivated to keep chugging on. And that's a super cool thing that people are finding value in. So we appreciate that. So I guess with that, we'll jump into today. We're at what, Tidy
53?
53,
yeah.
All right,
and I think we've got a really fun one. This is going to be a series of episodes that we're going to be doing. It seems we're kind of getting into these series of episodes because we're getting into content that's kind of hard to put into just a single episode, and we don't want to make these too long.
Yeah. So we've done a Shiny series and we've done a Plotly series, and now we're going to get into a classification series.
Yeah. So what are we classifying? You want to do that while I share my screen?
Yeah. While you fire it up. Yeah. So the issue we opened, I think, so 2 weeks ago we did the random forest classifier in Shiny, and that was a lot of fun. And in that episode, we kind of talked about like, gosh, we kind of built this model real quick. We didn't really compare it or blah, blah, blah. We should really do something.
Didn't really evaluate it. Yeah.
Yeah. So we opened an issue on the GitHub repo that said, why don't we do a series on classification models? And then at the end, we can do like one big powwow on comparing them and show different metrics and maybe build it into a cool GT table or something like that. So that's what we're going to start today. We'll probably do a couple weeks of different classification models. And what we're going to be classifying is PitchFX data. So PitchFX is Major League Baseball's tracking data of the pitch. And it tracks all kinds of features of the pitch, like the spin and the drop, the angles, and the speed, and the speed at the
whatever you want to know about that baseball, you probably will. They'll probably have something on it.
Exactly.
If you want to know when it was made.
Exactly.
What's the humidity in the air?
Exactly. Baseball keeps wonderful amounts of stats.
It's gorgeous.
We've used PitchFX before in our Plotly segment. Ellis wrote a really cool JSON data scraper. So it was like an introduction to JSON and
APIs
and
there's
then
a whole
Plotly,
mess of things.
We had the batter and the pitch type and all that kind of stuff, and that was really fun. So we decided to kind of look at pitch classification as our segment here for the next couple weeks. So the first thing always is to get some data. We used this really handy package called mlbgameday, which is like, I mean, literally you type in, you install the package, obviously, you use their function called get_payload, and you feed it a start and an end date, and you literally get the payload. You get a list of several different data sets for those dates. So you get pitch data, batter data, all kinds of stuff. So really cool package, really easy to use to get data. It just takes a while to download. Obviously, these are big data sets you're going to see in a second.
Yeah. So we've done this ahead of time.
We did this ahead of time, yeah. The other thing I did here was I threw some references. So I basically wrote this markdown as if I was kind of like going through it like for real, like someone dumped this data set on us and said like, hey, we have this question that we want to try and answer. Here would be kind of like a way that I would go about it. First is like, aside from talking to some domain experts, I'd get some references on like, what the heck am I looking at? So Fangraphs has a great webpage for PitchFX data, kind of gives you an overview of what it is, the types of pitches that are being classified, et cetera. And then I also found this paper. It's actually a PDF, which we can share on the YouTube. I can't remember what website it actually came from, but this guy, David Kagan, in 2008 wrote this cool article. I think he's a physicist. He wrote this cool article called Fun with PitchFX Data, and he goes over all the features, which was like super helpful in understanding what these features are telling you.
Yeah.
So found some references. So the problem statement that we have is that this fantasy baseball league wants to predict pitches that are thrown. And traditionally, the pitches are labeled by a human sitting in the stands or sitting in the broadcast booth. I don't know if the MLB does it like that. I don't know how they exactly label the pitches. Maybe they do it like that, or maybe it's more sophisticated. I'm not sure.
I'd hope so at this point, this day and age.
But yeah, exactly. But where we're at right now, the FBL would like to productionalize it and give it the classifications faster, get the classification faster. So they hired us. So yay. That's either good or bad.
Completely fictional. If there's any conflicts, completely fictional.
Exactly. We're going to start by loading in our data. So we're going to set this to the folder where we're housing the data, and we're going to run that. We're going to obviously set our options, etc., for the entire markdown. We're going to pull in a few quick packages: tidyverse, coreplot, and plotly. So really nothing crazy.
It's all stuff you've seen in the past.
We don't need the MLB game data package because we're not going to be downloading these live because they are large files. So I pre-downloaded the data. You can see the dates. I named the files the dates. I pre-downloaded the data and I saved them as RDS files, which is going to be way faster to load them in and handle than doing CSVs. So I bring in...
helps if I give the right path.
Yeah, there you go. Introduction. Yeah. Okay, there we go. So I load in set 1 and 2, which basically covers all of the pitches thrown from 4/21/2016 to 4/26. So
5 days.
5 days of data, but it's massive. And so I'm going to call that our train data set.
Yeah, we've got nearly 26,000 pitches here.
Yeah,
in 5 days.
In 5 days, yeah.
You pitchers be throwing.
Yeah, exactly. So we have a training data set, and then we have a testing data set, which is what we'll use to build our models off. So there's some of the names of the features. We're going to go over these in more detail when we produce our data quality report. This section here, this cleaning section, this is if I'm like working on this as a real problem in like real life. I always, in the start of our kind of session where I have the load the data, I always have this cleaning section, and this cleaning section I do iteratively. So as I go through exploratory data analysis, I make notes to myself about like, okay, this column needs to be cleaned up. I probably don't need these variables. There's a small number of them, like those kinds of things. That's what I'm doing in this cleaning section. So as we go through the exploratory data analysis, it's going to be on the raw data. It's going to be on the trained data set. But I would iteratively scroll back up as I make notes to myself and write this cleaning data set out, which is going to be the data set that I'm going to use in my analysis. It's going to contain the features that I'm going to use as my predictor variables, and it's going to contain the outcome variable of interest, in this case, pitch type. Mm-hmm. So we're gonna go through that iteratively. So we can run these right now. These are the cleaning steps that I did. The data was pretty good.
For the most part, yeah. I mean, just at a very high level, let's go here. We're filtering out pitch types KN, IN, PO, EP, FO, and we're also removing any cases where pitch type is NA. Just to make clean, don't worry about it. We already have specific values, and we'll go over why we're removing these pitches in the next step. And then we're selecting pitch type, start speed, end speed, and the other variables that we think are going to be important for prediction. And that's just what's happening here. There's not much.
the other cool thing that I will say, which you'll see when we produce our data quality report, is the number of NA pitches. If we build a model over the next couple weeks that we like, we can go back and take those NA pitches and classify them based on the features. So for whatever reason, they weren't classified. So we could do that, right? And that's kind of cool.
Mm-hmm.
So then checking for NAs, this is just a simple step. We've done this before. We're basically summarizing across all of the columns, and the function that we're passing that summarization across the columns is sum is NA for all columns. And then I just hit the transpose, the little T function there, so that it turns it into a long and skinny data frame.
As opposed to wide. It makes it just a little bit easier to look at. Otherwise it shows up like that. And if you have long data, it kind of becomes a little ugly.
Exactly. All right.
Into the EDA.
Yeah. SCIM-R we've used before. It's one of the coolest data quality reports you can find. So let's go all the way to the top.
Badoop. There we go.
So we see remember, this is the uncleaned data. So this is as if I was going through it for the first time. So it's the nearly 26,000 rows of data, 50 columns. The SCIM-R function breaks it up into variable types. So we'll see our character variables, our numeric variables, etc. So we have one factor, we have 29 numerics and 20 characters. So character variables, we kind of get a sense for
what's here,
what is there, and what number of missing, and how much percent of the variables are complete, and all that kind of stuff. Obviously, the pitch type is what we're most interested in here. Remember, we removed NAs in the cleaning set, or we will remove NAs in the cleaning set. The number of missing was only 36, so there wasn't a ton missing, but and then unique, there's 14 different pitch types in this uncleaned data set. And the white space thing is really nice, because if you have a lot of data cleaning to do and you have a bunch of variables with white space, you can always trim the white space so that you get rid of that stuff, and it helps you with filtering and things like that. Yay.
So I think a lot of these fields, description, type, TFS, these are all just character descriptions of what's going on here, and probably like URL. I don't think that's going to be super helpful for our prediction.
No. Yeah. Right.
So that this is like a good way to like get a lay of what's going on here, see what's character, see what's not. Go from there. Ooh, so this one's fun.
Variable factor.
So this one could be fun to use in the future.
The count, yeah.
Yeah. So what the count is: strikes and
balls, and we can pull in batters and hitters. There's a separate data frame that came out of the MLB game data package. We could do that. Mm-hmm. And then now we're into our variable types. So this is useful because, so for example, if we look at the n missing, things like spin direction and spin rate are entirely missing. So they're not going to be at all useful to us. So we're going to get rid of them. The main ones that we're concerned with are the things that tell us about the X. So how fast the ball is moving from the pitcher to the batter, X-axis movement, and then the Z-axis movement. So basically the vertical. Like a curveball is going to have some level of drop to it. Mm-hmm. Right? So and there's not much missing, only 36 values. So obviously this is a problem, right? Because right now we can see that the pitching, the pitch types that were missing, there were 36 of them. So it's just going to be a guess that the reason that they're missing is because they have no values.
No data.
Files, right? They have no pitch FX, whatever. The camera broke, or someone stepped in front of it, or Ellis spilled beer on it, or something like that. So,
oops.
Yeah. Oops. So we have some variables to work with. So if we go back to our script, one of the things I did was go to that Fangraphs data set, or actually it was from the PDF that the gentleman wrote, and I just wrote down some notes for ourselves. Usually when I'm doing this stuff, I just kind of take these notes and I put them off to the side in like a text editor so that I can always reference them, and we can expose our text editor.
Haha. Yeah, with the latest RStudio version, you can have multiple columns of source. And so I just copy and pasted everything over into a secondary panel here so that we can just keep this up with us and kind of close it and open it as it's useful for us, so we don't have to like scroll up in our script here to like, what was that note? Oh, I got to scroll back up to line 88 to see what's going on here. We can just kind of open it up and go, yes, here, this is what it means.
Yes.
So I'll just kind of hide that again for now
until we need it.
Until it's necessary, like the superhero we need.
So here, how many pitch types are there? The two little notes I wrote there, those are the cleaning notes, right? So I'm like, okay, we got to get rid of NAs, and there's a few pitch types that happen very infrequently. So PO, EPO, FO, basically everything after the KN, I'm just going to get rid of. It happens so infrequently compared to everything else. We could have lumped those. We could have done like an FCT lump and basically said group all these together, obviously except the NAs, which have no data. The only risk with that is you have to be pretty darn certain that those are actually similar. Otherwise, you have this group that has a mean and this massive amount of variance around it.
And then it's not actually helpful. Yeah. So in these cases, it's more valuable to remove them than just throwing it under the other category, because other then doesn't represent, like, it's not truly an other group. Yeah. It's just a smattering of, well, it didn't really fall. It didn't have a high enough count for us to really do anything with, but I didn't want to remove the data, and that's not helpful.
Yes.
Then it's detrimental to your analysis.
Correct.
So that's a good thing to note, though, when you're working on that. Cool. Sorry. So we got that. So we now know that we're going to remove. That's why we removed those pitches in the very beginning.
In the clean data, yeah.
And why we removed.
Data cleaning, yeah.
And of course we were going to move NAs, because if we don't have a called pitch type, we can't really use it for training.
So now we're left with these, I don't even know, 3, 6, 9 pitches, it looks like.
Yep.
These are the outcome variables of interest. We're trying to classify a pitch to be one of these 9 types. And what we want to do is we want to get a sense for what are the distribution of data for each of our predictor variables for these pitch types? Like, is it going to be helpful and discerning? So I make a little note there that now I'm going to use our clean data set to look at this. And I'm just going to write a quick function to start so that I don't have to copy and paste a ton of data. So this function is basically taking one variable. It's a single variable function, and it's taking an X variable, which is going to be the predictor variable that we want to look at the distribution of. And so within that function, it's going to use the train cleaned data set, and it's going to build us a ggplot with that X variable, obviously, on the X axis, so it's properly named. And then we're going to have on the Y variable, so these are going to be horizontal box plots with the pitch type ordered by the X variable median within that box plot.
All right, so I'll make that function.
And we can run that function over all of these different, you could have done this in different ways. You could build a for loop and print it out to like a PDF or, however you want to do it. Yeah. I just did it really kind of quick and dirty. And I make a little note down there at the bottom, which basically says for us to think about as we're going through our classification, is those two variables XO and ZO, which I think are the 50 feet speed. I think it's like velocity, or
let's quickly bring our handy dandy.
Yeah.
X0 and Z0 position at 50 feet.
So this is the X position and the Z position at 50 feet. They seem to not be very discerning. Like the median value and the box plot, even the variance of the interquartile range, the variability or the width of the interquartile range is relatively similar for every single one of those variables. Mm-hmm. So they might not be useful metrics going forward. So I just make a note of that to be aware of. And then a final kind of measure of in this EDA, even though the Pearson correlation is indeed a true stat. You can read studies that just have Pearson correlation. It is a good kind of descriptive. I tend to use it as like a descriptive measure of our data. So I create a table of the correlation coefficient using the core function. with that -1 just basically means remove the first column, which is a list of the pitch types, which obviously are not numeric. So there's no need to do a correlation over those. So I build this so that I built this in its own little matrix, correlation matrix, so that I could feed it into this core plot dot mixed. The mixed part being that there's going to be some graphics and some numbers based offset of the diagonal. And you'll see what I mean here in a second. When we run that.
So lower call black, TLCX.
Yep. Which is going to be the size of the values, the size of the column names is the TLCX. The lower call black is that I just don't want the lower column to be colored because I find it, like, at least for me, hard to read. I can see the colors on the top part. So really quickly, you can look for the different dots that might be of interest. For example, we've got VZO and start speed. And we can see that they're, by the dot color, it's red. So that means it's going to be negatively correlated. And it's relatively large. So now we can kind of drill into that actual, it'll be the bottom left, all the way the bottom left correlation coefficient of negative 0.56. So start speed and VZO are going to be negatively correlated. Start speed is obviously the speed at the, the speed from 0 to 50 feet. So from the pitcher's release to 50 feet. Mm-hmm. And then the VZO is the velocity
in the Z
on
direction.
The Z-axis at 50 feet. So why would they be negatively correlated? Well, probably because the start speed, if the start speed is that fast, the person is throwing a fastball, which tend to be pretty straight line pitches. They're going to have much less of a drop than like a curveball, which is going to fall off the table or something like that. So that kind of makes sense. So this is a way to start to look at your data. And then with that, we get into kind of our first beginning of our
what do we got here?
Classification models. And we're going to use an unsupervised approach to start. And then we're going to get into supervised approaches in the next couple weeks.
Yep.
So we're going to start with hierarchical cluster analysis. And this is we talked about k-means cluster analysis and PCA, which are two other kind of unsupervised techniques in the X-Men episode. Mm-hmm. Hierarchical cluster analysis is a little bit different. So k-means, if you remember, we pre-specify the clusters, and then k-means works by randomly choosing the starting point and then building centroids from there and then building clusters around that. So that's why we set the seed and did all that kind of stuff. Hierarchical is a bottom-up approach. And so for hierarchical clustering, you don't need to pre-specify any number of clusters. Basically, it's going to treat each piece of data, each observation as its own, and then it's going to build from there until all the data is fit. And so it's a two-step process where you first choose a dissimilarity matrix or a dissimilarity metric, which is basically telling us, hey, identify how close each individual point is to these other points, and then build clusters. And then from there, you need to then choose a metric which helps us, a distance metric for the differences between points, a dissimilarity metrics for the difference between the actual clusters. So once clusters are built, how different are those clusters? Yeah. So we'll do that. So Ellis, you want to go through this little piece here?
Thing. Yeah. So what we're going to do is we're going to take our clean data here. We're going to group by pitch. So now any step that we do, think of it as if we plucked out a data frame of just that pitch, and now we're going to assign stuff to it. So now we're going to use summarize. So what summarize is going to do is it's going to take that data frame and collapse it down into a single record. Now we're going to go use across. So now we can define, okay, what columns do we want to apply this to? And in this case, we're just defining everything. So across every column, we're going to apply a function. In this case, we're going to use the function median. So this is going to calculate the median value of every pitch across every column. So we're going to now run that. And so now we're going to get a data frame that looks like this. So we've got our pitch type, but we've only got now one row for each pitch type. And we've now taken the median of start speed, end speed, PFX, X, PFX, Z, all the way down to VZ0.
So we basically built a table of summary features. We could have built other summary features as well. We could have put like standard deviation in here and things like, or variance, or since we're using the median, we could put variables about the interquartile range, the 25th and the 75th. This is very data reduction-esque. We went from nearly 26,000 rows to 9 under the assumption that change-ups are generally going to be, on average, this speed, this PFX, this PFXZ, et cetera, et cetera.
Yeah. We're assuming similarity between the groups and that we can cluster. Yeah. We're assuming we can cluster by group, which we're trying to classify by pitch type. So, gosh darn, I really hope we can.
Hopefully, yeah.
That assumption needs to hold.
Yeah.
And so we're going to extract the pitch type out of here, so just so we have that on its own, because we're going to need to drop that in a second here. So now we're going to create the table that is specifically going to be used for clustering. We're going to use that pitch type summary, so this data set here, and we're going to remove the pitch type because that's not, we can't put character vectors into this data set here. And then we're going to convert it into a data frame just so it's nice and clean. And so we end up with our cluster.df, which is that same exact thing, but now it's just a nice data frame. And we're going to assign the row names, because data frames can have row names, the pitches. So we're still going to preserve that information of pitch type, but it doesn't exist in the data itself now. It's now a row name, which there are opinions about row names that exist in the world in R about whether they're good or bad.
I generally think they're bad. The only reason I did it here is because the plotly dendrogram function can only plot on the labels if they're in as row names. You can't feed it a labels vector.
Interesting.
So that's the only reason. Otherwise, I would never do it,
yeah.
And I don't recommend anyone ever do it. I simply did it just
especially because if a row name actually means something, it should be a column.
Correct.
If it's not, you should only be using it as a row name if it doesn't. I mean, you're just trying to select unique rows. Here, correct. Row name does mean something. It's not just, it's just a unique row identifier. No, it's like, sorry, right. Tangent. It's just a thing that I like to bring up that I think about a lot. A weird amount. I don't know why I think about it that much. But yeah, so now we're going to take this cluster DF and we're going to scale it. So that means each column is now going to be scaled from, I think, 0 to 1, correct? Or no?
Yeah, so it's basically we're going to produce a z-score. And the reason why you want to do this with clustering is if you had a value that was like really high, let's say we had like pitchers' body weights in there, relative to these small values, if we were to not scale the data and just run, let's say, the Euclidean distance over, those high values are going to drown out the lower values and might assume more weight. So we want to put everything on the same scale. And the dist function we're going to use is Euclidean distance. So this is identifying the distance between each of those points, the mathematical distance between each of those points, with the idea that the smaller the value, the closer the distance.
Mm-hmm. So now we end up with this vector. What type of object is this?
Is it a matrix?
Dist. It's a dist class.
Dist. It's a dist object.
Which, I mean, probably under the hood, it's probably a matrix or whatever it is. And now we're going to throw that into the hclust function using the method ward.d. Patrick, this sounds oddly similar to your last name.
Yeah, I didn't write this. I'm not even related to the person who wrote it. I wish I was.
So why use this method?
There's a number of different methods that you could select for dissimilarity. Remember, dissimilarity is once you've identified the points that are closest together, you want to identify the differences between the clusters. That's the bottom-up approach of hierarchical analysis. So you could have used like averages or centroid or different dissimilarity matrix. The Ward D is a popular one that often gets used, and one of the reasons why I like it is it's a minimum variance method, which means that just like K-means clustering, which we've used before, It's trying to minimize the within cluster sum of squares. So it's trying to minimize the difference between the values within the cluster to the mean of that cluster. So I do use that because it does tend to look similar to k-means in terms of identifying the similar clusters without having to pre-specify a set number of clusters like k-means uses. So in my head, it makes sense a little bit.
Cool.
Yeah.
So now we end up with this fit here that we're going to then throw into plot. And so it has a plotting method for this object here. We're going to set the labels to be pitches and set the label to be pitch FX clusters. Feature up. There we go. Alrighty.
Yay.
So there we go. So you can see now how the different types of pitches are going to be clustered here. So let's quickly bring over a handy dandy descriptor of the pitch types here. So it looks like CU and KC are going to be grouped together. So that'd be curveball and knuckle curve.
2 off-speed pitches.
That makes sense. You know, curve.
With have like movement on the z-axis.
Yep.
Right?
Looks like FF, FT, and SI. So sinkers, 4-seam fastballs, and FT.
2 seams.
2-seam fastball. So yeah, 2-seam. 4-seam fastball. I mean, that quick gut check. Group. That makes sense. CH and FS. Which ones are those? Changeup and split finger fastball. So I would have thought split finger would cluster with the fastballs, but I guess its characteristics, even though it's considered a fastball, is more similar to a changeup. Based on the data that we have.
Fastball is thrown at a slower speed. I don't know.
Yeah, I don't know.
That's something we could actually, the start speed or the speed at 50, we could look at in our box plot and see the difference between those 2 pitches. Like maybe there is a difference. Maybe there's no difference rather.
I don't know. Yeah. And then finally we have FC and SL. So FC is cutter and SL is slider. So apparently they're related.
In some way, yeah.
In some way, shape, or form.
Yeah.
Alrighty, so that's our clustering there.
There we go.
Here we go.
So it looks like we have 4 clusters.
Sorry, it moves around when I try to make it wider here. So yeah, it looks like the 4 clusters. Let's make them more unique. Sorry, this line is the same line as this one.
Oh, so. You said K equals 5 there in the rect.
Sorry, let's boom, there we go. Ignore what I just did.
Let's we go.
See? So we've got those 4 clusters here that it's recognizing. Here's the four groups here.
So the interesting thing that's the thing about hierarchical cluster analysis is, if you remember the k-means episode, we did like a scree plot and we looked for the elbow and tried to determine where, the best number of clusters would be. In hierarchical cluster analysis, we're not predefining that. So we've basically looked at this and we said, it looks like there's kind of 4 clumps of data. That makes sense. And you would probably do this and you'd put the red border around that. And then you'd sit down with a domain expert, like a pitching domain expert. And you say, like, what do you think about? Like, does it make sense that these things are together? And maybe they'll say, well, no, there's probably a little bit more separation between a few of these. So you could change the number of K, the number of clusters. If you change it to 5, now there's a little separation in that furthest cluster there where we see the FC, which was our cutter, and the SL, which is our slider. They actually separate a little bit based on some of the median values. Remember, all we used was the median in our data, in our reduced data set there. So it's important to keep in mind. We didn't account for any other features which we could have done.
We didn't account for variability. We didn't account for everything. But this is saying that FC and SL are more dissimilar than FF versus the FTSI group.
Yes. Yeah.
Based on the average values that we pass to it.
Correct.
To be very clear. Cool. All right. So now we've got our clustering here. Now what do we do?
Well, we can look a little bit deeper at this. We can create the actual cluster assignment. So we'll stick with 4 for the purposes here. So we use the CU tree function, and we pass it our pitch clust final data. And so basically it's going to identify. So like CU and KC are together in a cluster, they're in cluster 2. So we could see CU is 2 and KC is 2. And so you could see that it just basically assigned the labels to the pitch types. And I'm just going to throw that all into a single data frame itself. So we basically did like a bind columns where I took the pitch labels, I took the cluster data frame that we had created, and I took the cluster assignments, and I create this flat table that tells us the information about the cluster types and the pitch types, etc.
Everything that we could possibly want.
Yeah. So let's go ahead and look at which pitches are in each cluster. We kind of did that with a little table there. It's the same information. And now we want to do some summarizing by the clusters. So this is a little bit of a tricky one, a tricky piece of code, but it's really handy. So we take the pitch cluster data frame that we just created, and we're going to group it by the cluster numbers, so 1 through 4. And just like before, we're going to do this summarize across, where we're going to say, I want to use the column start speed to VZO. So all the numeric columns minus the pitch type and the cluster type. And I want to create the mean and the standard deviation. Now, if we ran it just like that, we get this horribly long table, which to me, yeah, it's really wide. It's hard for me to look at this and understand it. So the first thing that I do is I pivot the entire thing longer, just removing the cluster number from the pivoting. So basically it's taking the names of the features and the values, and it's saying, hey, spin these out into a long table. And so that looks somewhat helpful, but not entirely helpful, because what I then want to do is pivot it back wider by saying, take the cluster numbers and make those the columns, and then take the values and make those the values within each column. And now I can look down this long data frame where we have 1 row per feature for average and standard deviation, and then we can look across the cluster numbers. So we can see here, cluster 4, which contained our 3 fastball type pitches, indeed has the highest median speed and the lowest amount of variability. So those pitches are throwing fast, and there's not a lot of wiggle room around them.
Yeah. Meanwhile, cluster 3, which was the one that like had those 2 that immediately, once we said, hey, give us 5 groups, it's like separated them out. It had kind of the median, like a middle amount of speed out of the 4 clusters. It was like in the middle there, but it had the highest standard deviation.
Yep.
So that means that cluster probably wasn't. I mean, we kind of already knew this. Isn't very clearly defining that group.
Yeah, and if you look at its PFXZ average, it's also kind of right in the middle between the the values of PFXZ for these other variables. And you can again see that it does have a high variability to it. So that's its movement on the up and down axes, right?
Mm-hmm. So it's just they're actually different pitches, but because we selected 4, those are the more similar to each other than they were to other ones.
Yeah, correct. All right.
Cool.
So that's kind of cool. So now we have that, and we can make this a little more pretty. We can do it in Plotly, so we can take our pitch final cluster data and make it this object as a dendrogram, and then we're going to plot. So we use plot dendro, which is a Plotly function, and we pass it that dendrogram object. I set the height and the X min so that it spaces it out, otherwise it kind of shrinks it down. I hide the legend because it doesn't give us any extra information. And I'm going to add this little highlighting tool. So anytime that we select something within the graph, it's going to highlight it. And the persistent is true and the dynamic is true allows us to have the option to change the brush color and then to maintain the color as we change. If we hold the shift down, we can kind of select other colors. So you can select nodes, or you can highlight over a group of pitches. And so if you were like taking this to a presentation, you could basically like highlight over a group of pitches and talk about like maybe you have a table or something off in the right column that shows you the average values, and you could throw this into a Shiny probably and make it interactive and get a table and other information that talks about your data in a meaningful way to a decision maker. But this is just an interactive way to mess around with the dendrogram.
Exactly. Super fun to play around with.
So I think the last piece is we can just alternatively take all of the data. We're not going to produce the dendrogram on this because it's big enough, but we can take all the data and we can do the exact same thing. So you want to walk through this one?
Yep, sure. We're going to
basically the same steps.
Pull out the pitches, so a vector of all the different pitches that we did. We're going to then do the same exact thing. We're going to convert it into a data frame and remove the pitch type so that it's just a numeric, or it's only got numeric values. Throw it back into the scale and dist so that we end up with the distance matrix for each individual pitch. So how close is pitch 1 versus pitch 10? And this is going to take a little time to chunk through because it's got to do every comparison. It's now done. Thank you, computer, for making me look silly. Now we're going to throw it into hclust to create the dissimilarity matrix using the same word method as before. We're going to now pull out, we're going to assume that we're going to be using 4 groupings again, like we did in the prior method here. So we're going to pull out that, I guess it's still running hclust, it's still calculating the dissimilarity.
It'll chug for a second here.
There we go. There, pulled out the cluster assignment, so this is which group is each pitch in. And then we're going to bind it all together, just like we did before. So pitch type is going to be pitches. We're going to take that clustdf. We're going to add cluster number and assign that. So now we end up with a long data frame of pitch type for each pitch, every single pitch. What pitch type, start speed, end speed, the various metrics that we have, and which cluster number that they live at, that we've assigned them to, given that we have 4 clusters. And so now we can summarize them. So now we can go through, and now that we've assigned it all and done our analysis, now we can kind of evaluate what we did. So we're going to take this, the pitch clustdf, remove pitch type again, because we keep on adding it and removing it. We're going to group by the cluster number. So now that we can, for each cluster, go across each of the metrics, so start speed all the way to be z0, and take a list and get the mean and standard deviation and record those, and then do the same long wide thing that Patrick just did here in the prior step. But now we're using all of the pitches, and so now it's not having summarized information for each pitch group and then looking at it. It is going all the pitches that we assigned into group number 4. What was their average speed and what was their average standard deviation? And so this should give us a better idea of, across all our pitches, what does it look like, not having reduced it down to only looking at the pitches that it was assigned to, so we're not preconceived assigning information to it. And so here you can start seeing like different patterns in here. Like for pitch or group number 3, it's heavily negative for the PFX Z average.
Yeah.
Compared to
group number 3 is going to be all the change up or the all the off speed, like the knuckler and the curveball. I think the knuckle and curveball make up wholly group 3. We can look at that here in the next step. But
yeah, so you can look at that. Or group number 4, the velocity X average is very, very negative in group 4 here. So like you can start seeing like, oh, here is the different ones here, or like group 1 here has the highest average start speed. So it's probably the fastballs.
And the end speed, right? Which was, if you remember a correlation matrix, start speed and end speed were really highly correlated. And that tended to be your fastball type pitches, right?
Mm-hmm. So you can kind of look through here, and I've actually been on projects where we will send like an expert a summary like this, where we've done our clustering of everything, and we let them tell us, oh yeah, that makes sense because this is this, and then this lines up with this here. This totally jives with my understanding, and they're an expert, so we trust them, of the way that these things work.
And also then in a 2-step process, you can use these clusters in other models, and you can give the clusters names, right? Like cluster 1 might be like fastball type pitches or speed pitches or something like that based on the descriptive features of that column. So you give it a meaningful name, and once it takes on that meaningful name, you might be able to then use it downstream in other analysis to derive more information from your data.
Yeah, exactly. All right, so we've got those summaries. So now which pitches ended up actually in each clusters, because we do have the labels in this case.
Yeah.
So this would be more like of an unsupervised situation here, but now because we do have the labels, we're able to look at that. And so let's look at our little table here. Let's zoom in a little bit, and let's also bring over our handy dandy pitch types over here. So sorry, this looks ugly, but I want to be able to see everything very clearly here. Alrighty, so we got here. So group 1, wow, 7,000 of the 4-seam fastballs ended there. FT, which were the 2-seam fastballs. SI, sinkers.
Pretty much all your speed, your fast, as we saw, highest start and end speed. Your fastball-esque pitches tended to fall in this category.
Yeah.
Category 2 seems a little bit less.
It's kind of a catch-all.
Sure. Yeah, less sure.
I mean, it's got the sliders and the change-up.
Yeah, that's true. Yeah, there's a bit more off-speed pitches in here, but there's also a few others. One thing to think about with this, which we didn't put in the model, but we could, maybe down the road, is different pitchers, like the characteristics of a different pitcher. So there might be a pitcher whose fastball just isn't as fast as someone else's fastball, in which case it might end up being in a different category based on its pitch FX features, because it's slower, because it moves more, or because it moves less. Things like that can sometimes be an added bit of information that you want to try and account for.
Mm-hmm. Yeah. So yeah, it's just like inherent changes in the pitcher themselves that can impact this classification here that we didn't account for. Or like group 3 definitely is like change up.
Yeah,
like it's
way
change
off
up
speed pitches.
Yeah.
Change up the knuckle curve.
The knuckle curve, like most in there. It's got sliders in there, but slider I think would definitely more likely fall under category 2. So
yeah.
Cool.
So then we can finally just plot this. One last step before we end is this plot. So basically what I did here is I tried to take the pitch types and I mash them down to fastball and off-speed pitches. And I'm going to take the pitch cluster data. I want to count the pitch type in each of the cluster numbers. And then I'm going to mutate. I'm going to create a column that says when the pitch type is FF, FT, FC, SI, or FS, we're going to call it a fastball pitch. And anytime it's anything else, we're going to call it an off-speed pitch, because that's what it is. And then we're going to group this by the, or we're going to ggplot this by the cluster number on the x-axis. The y-axis is the n, so that's the count that we got from our count function, and we're going to fill it by group. And what I'm trying to do is I'm trying to see, do any of these clusters different or have more concentration of fastball pitches or off-speed pitches, which is basically a way of trying to look at the table that we just went through in a more broadly grouped way.
Computer is struggle busing right now.
I think you gotta maybe drag more. Huh?
Invalid graphic state.
Do dev.off. Like just get rid of the graphic.
Yeah, turn that off. Yeah. Oh, I wonder if it was the the Plotly.
Oh,
confused
maybe.
It still thought it was supposed to be running.
Okay.
Cool.
So here we go. So this is kind of cool, right? So as we looked at in the table, we have now a different picture of what our cluster analysis did. Remember, this is on the training data, right? So we have cluster number 1 contains almost wholly the fastballs, like the fastball type pitches, right?
Mm-hmm.
Whereas the 2 in the middle, cluster 2 and 3, tend to contain the off-speed pitches. Cluster 3 was like the knuckle curves and the curve balls almost exclusively. And then cluster 4 is a little bit of a mishmash of things, but tends to contain the fastballs, maybe these are fastballs that have some movement to them that are similar on the z-axis to some of the off-speed pitches. But
the pitcher might throw a little funny, or
exactly,
a little bit slower. Like we said, we didn't account for pitcher, so not normalized for that. But there you go. So this is a way to visualize your clustering at a higher level too.
Yes, yeah.
With contextual knowledge.
Correct. So we kind of have these so things we could do going forward. We're going to do some classification type of stuff, and we have some models that we're going to build on this. As we talked about with the cluster analysis, this is kind of descriptive. It's unsupervised. We had no outcome of interest. We're trying to see where the data lies. One thing we could do is take these cluster assignments and use the training data set or use that information to then make a forecast on the test data set based on the features of which assignment into these clusters they'd be in. So, this is a cluster 4. It could be like a fastball type pitch with movement, with off-speed z-axis movement, versus this is a cluster 1, which is pretty much exclusively a guy throwing gas. Like he's just throwing the heater, and that's what it is.
Just getting it done, getting it down.
Just getting it done, right?
Boom, there you go.
That's some ways that you can use the hierarchical cluster analysis as a descriptive feature, but you could also use it downstream as a bit of information in a secondary model.
Boom. Well, there you go. There's some information on this data that we're going to be looking at over the next couple of weeks, and like an initial look at it. Like what's going on here? What can we start? What trends can we start to see in this? What's interesting to us so far? And cool. With that, we're going to call it. So thank you so much for joining us for episode 53. As always, my name is Ellis Hughes, and you can find me on Twitter at Ellis_Hughes.
And I'm Patrick Ward. You can find me on Twitter at OSPPatrick. You can hit us up on Twitter at tidy_explained, or email us tidy.explained@gmail.com, or comment and subscribe on the YouTube channel, take out an issue on the GitHub repo. Any of those ways, whatever is easiest and most comfortable to you, feel free to shoot us some info.
All right. Thank you all so much, and keep on exploring your world.